Hello everyone, this is ML Naruto. Welcome to my channel. So, uh, let me draw some kind of plot here. Okay. So, what if this is our independent variable x, and what if this is our dependent variable y? Okay. Whenever you are given a dataset like this here, this is this is my dependent variable, that is y, and these are my independent variables that are x1, x2, x3, and so on. Okay. So whenever you are given a dataset like this, so these are independent variables and this is dependent variable, which are nothing but commonly we can call it as columns. Okay, these are all the columns here. And what are these lines here? Inside these lines, we will have some kind of values. Okay, some kind of numbers. Those are nothing but the data points, or you can also call it as rows. Okay, so whenever you are given a dataset like this, first of all you need to understand, does this rows and columns are enough to capture the relationship between the x and the y here, right? So if you are given a dataset like this, you need to think that these rows and columns are sufficient to capture the or to establish a relationship between the x and y. Are these sufficient or not? You need to think of this. Why? Because let's imagine here how many rows I have here. Let's say 1, 2, 3, 4, 5, and 6 here. Okay, and how many columns do I have here, and so on, right? Let's imagine here I have the column still some x20. Okay, for example, these are the 20 columns, and this y, along with the y, you will have the columns you have is you have some 21, and you only have the rows that is equal to 6. Okay, so this is the kind of a data you have. So first of all, when you look at these columns and when you look at these rows, you need to understand whether these rows and columns are sufficient or enough to establish a relationship between x and y. I mean, does these I mean do these permutation, I mean, do these columns and rows will explain are enough to explain the relationship that is been involved in the x and y? You need to think of this. This is a major situation where most of the time you will be having maximum rows. Okay, most of the time you will be having maximum rows, minimum columns. Okay, most of the time you will be having this kind of a situation, but only very few times you will end up having this kind of a data set. Okay, where you will be having so many very little amount of rows, that is maybe here there are only 6 rows, but here you will have some 21 columns, right? So if you find this kind of a situation, this situation will create a kind of a thing which is nothing but the curse of dimensionality. Okay, whenever you find any such kind of a situation, that situation will leads your model towards this curse of dimensionality. So what is this kind curse of dimensionality? I'll explain, no worries. Okay, so for example, so this is my x, this is my y, and I have data like this. Okay, so like this, whenever I want to, so if I want to draw a straight line, my best fit line, so how can I mean, how can I do justice on this kind of a data? So maybe like this here. So this would be the best fit line. Okay, but when you observe carefully here, see, there is so much kind of gap here. Okay, each data point is spread, each data point is spread across the x-axis and the y-axis, and it is having so much kind of distance in between those data points. Okay, see here, the distance is very high. Okay, Each data point is having actually so much kind of distance here. So if you have the situation like this, okay, then what happens is it may falls into the category of curse of dimensionality. So what does that actually mean? I'll tell you. For example, you have many features, okay, you have many features, but only very few, rows or data points, you can call, or data points, okay, or data points, okay. You only have very few data points, and which are very far from a, see, these are actually very far. See here, these are actually very far from each other, okay. These are our data points, that is, these particular points are nothing but our rows here, okay. These are our data points, and I have already said I have many features, right? So let's imagine this is the x1 here, this may be the x2 here, this may be my x3, and so on, okay. I have too many kind of features. That means I'll be having too many kind of x-axis, but only one y-axis, and my data points are very few here. See, just concentrate here, very few rows. That is, my data points are very much lesser here. That means if I have some uh, 26 columns, that is, if I have 26 columns like x1, x2, and so on, x26 I have, but I only have the data points, that is my rows, equal to some kind of only six rows. Those are the rows. These are the rows here: 1 and 2 and 3 and 4 and 5 and 6 here, okay. So what happens is our algorithm can't find what kind of a surface to be drawn in these areas. Why? Because there is a large amount of gap here. Just observe carefully. See, the gap here, the gap, here is very much high. So if the gap is very much high, our algorithm may get confused. It doesn't know what kind of a shape to be drawn. So it will just end up drawing a simple straight lines, okay, with the sharp peaks and valleys. So what happens is, see, I'll tell you. See, if you have a data like this, then our algorithm may get confused, and what it will draw is, let's imagine you have a plot like this, okay, and you have the data which is very much far, okay. It's actually lying far here, far from each other. You have a data like this, very much far and very less data point actually. So your algorithm won't find a perfect shape to draw. I mean, how does it draw? It actually try. If it draws a straight line, will it be a best fit line, which is actually capturing all the data points here? No. Why? Because just imagine, just look at here. All the data points should lie on the same line, or all the data points should actually lie very much closer to the line. But is it happening here? No. Why? Because each data point is actually lying very far from this particular line. So here drawing a best fit straight line would be meaningless. So what happens here? It just confused. It just get confused. The algorithm will get confused. So what it will do is it will just draw a straight kind of a line on the possible data points like this. Okay, so it will draw the data. It will draw a kind of straight lines, straight surface, or whatever you call. Okay, here I'm saying straight line. Why? Because here I'm just considering only one independent variable and one dependent variable. Okay, if you have too many kind of variables like this, it would be the straight kind of a surface. Okay, straight plane, you may call it as, not a straight line. Okay, depends upon the variables, the shape actually change. Okay, so if it draws like this, okay, see, algorithm will get confused, and it doesn't know what kind of shape to be drawn in such a kind of situation. So it just simply considers, uh, it just simply by default it will draws a simple kind of a straight line like this, joining each and every point like this. Okay, it has many sharps and peaks here. See, this is a kind of a sharp peak and this is a kind of sharp valley here. So each kind of a line is actually having sharp peaks and valleys. Okay, so if the model touches each and every data point so perfectly in the training, that means, for example, if we have data like this, okay, see, I'll tell you. Okay, here just imagine here in the first figure, we have a data set like this. Our model will tries to draw a simple straight line on each and every data point. So like this. Okay, so if our algorithm tries to fit the data points exactly with these sharp peaks and valleys, then what happens is we will get the we will get the model accuracy. We will get the model accuracy that is 100% on our trained data. Okay, when you try to fit a trained data for our model, you will get the 100% accuracy on this kind of a data. Why? Because it is actually fitting all the data points so perfectly. See here, it's actually drawing all the straight lines and it is actually connecting each and every data point so perfectly. So you'll end up having 100% accuracy on the trained data. Okay, but whenever you try to fit the test data, okay, but in test data, that is an unseen data, maybe the production data, then what happens is data points are from the universe, right? So it hasn't seen the data yet. So this is the data which it has already experienced. So it will try to fit the line, try to fit the best fit line so perfectly on each and every data point. But here the data is the test data, and all the data points are actually unseen. So algorithm won't know what kind of a data is. So it will definitely gives you the lower accuracy. Then the model accuracy would become approximately low on test data. Why? Because we may take multiple samples from the population, right? So when we take multiple samples from the population, now due to this, the accuracy will go down and it will reaches to the accuracy which is less than the trained data. On trained data, if you get 100% accuracy, on the test data, you will only get maybe 70% accuracy here. Okay, this is happening due to the curse of dimensionality. Okay, this is happening due to the curse of dimensionality. We can say that our model is suffering from the variance error. That is, our model is not stable. It is unstable and it's almost a risky model to perform. If you consider this model, and if you consider this model and in the deployment, it will give you 100% accuracy on the trained data. Okay, but whenever an unseen data is occurred, then it will automatically gives you the accuracy which is lower than the before a previous accuracy, which is the on the test data, it may give 70% or 60% accuracy, which is very much lesser than this trained accuracy, right? So this is the problem which you may occur for the result of curse of dimensionality. So you have got to know that what is meant by curse of dimensionality and what is the problem created by the curse of dimensionality. Now you need to know what is the solution here. Now you need to know what is the uh, Now you need to know what is the solution here. So the solution would be, you can encounter this curse of dimensionality using the following ways. That is the PCA, nothing but principal component analysis. So using the principal component analysis, you can find out. So you can encounter it, and the second one is using the regularization. Using the regularization techniques, which is nothing but the lasso and ridge regression here. Lasso and ridge regression here. It can also be called as the shrinkage models here. Shrinkage methods. Okay. You can also call it as shrinkage methods. And you can also do that using some kind of visual analysis. Okay. You can also do that. You can also encounter this using visual analysis. Okay. So this is the scenario here. You can also encounter using PCA regularization techniques, or you can also call it as lasso ridge, or you can also call it as shrinkage methods. And third one is visual analysis. By using these three kind of methods, you can encounter this curse of dimensionality. Okay. But one thing you need to understand is whenever I say, okay, whenever I say, so how does the curse of dimensionality will happen usually? This is just a reminder. So this is a curse of dimensionality. Let's imagine. So how does it actually occur? When the columns are higher, okay. When the columns are more, rows are very few. Okay. So if it is the case here, if it is the case here, then your model will end up having situation which is nothing but the curse of dimensionality. Okay. So whenever I say columns are more, that doesn't mean x1, x2, x3, x4 and so on, x26. No, this is not the situation. Whenever I say columns are more, that means using the existed columns, what if you create another additional columns? Okay, for example, I have the columns x1, x2 and x3. Okay, and I tried to create x4 using x1 plus x2. Okay, I tried to sum up x1 plus x2 and I have got the another column, that is x4. Okay, likewise, if I end up creating multiple columns, and that may leads to, for example, if I have so many columns, maybe some 70 columns. Okay, I have ended up creating 70 possible columns from the existed columns. Okay, x1, x2, x3 are only the first existed columns here. But when I try to use so many kind of formulas, that is x1 plus x2, or I want to club x2 and x3, or I want to club x3 and x1. So using all the permutations and combinations, I end up created x1, x2, and so on, x70. Okay, this is just an example. Okay, so if you are having, if you are end up creating multiple columns out of the existed columns, and you will only have, if you only have a very limited number of data points, that is nothing but very, if you only have very limited number of rows here, then that situation would fall into the kind of a situation which is nothing but the curse of dimensionality. Okay, this is the scenario. Okay, so yes, that's all for this video, and in the next video I'll be explaining what is meant by a shrinkage methods, and I have already explained shrinkage methods are also useful in encountering the curse of dimensionality situation here. So I'll be explaining all the shrinkage methods, their usage, and their learning process under the math behind those shrinkage methods, that is lasso and ridge regression. So the uh, behavior of those methods, uh, with the help of so many diagrams and so many math formulas, I'll be explaining that in the next video. So yeah, that's all for this video. I hope you have got better idea about the curse of dimensionality, and in the next, I'll see you all in the next video. Okay, bye, take care, Jai Hind.